In this video, we're going to talk about acids and bases. These are your learning targets. Let's first start with some examples of acids and bases. Probably one of the first things that come to mind are cleaning products like bleach. Bleach is a base. Shampoo is a base. What's acidic? We have citric acid, right? Lemons, oranges. You might remember acetic acid, right? Vinegar. Here are some other examples. Hydrangea flowers. You might have seen these flowers around your neighborhood. Maybe you have it in your own backyard. Hydrangea flowers can vary in color. You might have seen them in purple, pink, white, or blue. Well, the colors will depend on the acidity of the soil. So if you know someone who likes a plant, you'll see them actually measure the pH of their soil because it can actually kill their plants or it can help their plants thrive. So they really want to know the pH of the soil. Ants release formic acid to alert the entire colony of danger. We've all heard of acid rain, and acid rain can destroy buildings and statues. We have acid in our foods and drinks. We use it to flavor it. Again, just going back to the lemons, we have citric acid, right? And then we have stomach acid to help us digest our food, and amino acids make up every organ in our body. So now let's go over the difference between acids and bases. Acids contain hydrogen ions. If you take a look at some of the examples that you have on your note paper, some of the acids are like HCl, hydrochloric acid, HNO3, nitric acid, H2CO3, carbonic acid. So what is similar amongst all these examples? They all have hydrogen, they all begin with hydrogen, right? So they all contain hydrogen ions. They taste sour, they are corrosive to metals, they have a low pH, so anything less than a pH of 7, so remember a pH scale goes from 0 to 14. They become less acidic when mixed with bases, and they turn blue litmus paper red. So you might remember that there's pH paper, where if you dip it in a substance, it'll change color and it'll tell you what pH level the substance is. Well, litmus is just a type of dye. And so you have blue litmus paper and you have red litmus paper. If you put it into a substance and it turns red, then that tells you that it's an acid. So now let's talk about bases. Bases contain hydroxide ions, hydroxide OH minus 1. So if you take a look at your examples again, you have NaOH, sodium hydroxide, CaOH2, calcium hydroxide, BaOH2, barium hydroxide. So what do these substances have in common? They have the hydroxide in common, right? Bases taste bitter, they're chalky, they're slippery, they have a pH greater than 7, they become less basic when mixed with acids, and they will turn red litmus paper blue. And to help you remember that, just think of basic blue. Bases turn the red litmus paper blue. So let me show you the simulation. And this simulation is not litmus paper, this is actually pH paper, and here's the pH color key, but I just want to show you that, I mean, similar to this pH paper, litmus paper, again, if it turns red, then it tells you that it's an acid. If it turns blue, then it tells you that it's a base. Again, it's just a simple test to tell you if a substance is an acid or base. So I dip the paper in, there we have reddish color, right? And so that tells us that it's an acid, whereas a base will turn the paper blue. Okay, and then in between acid and base we have something that's neutral, right? And the prime example of something that's neutral is water, and water contains equal concentrations of hydrogen ions and hydroxide ions. So water, the water's dissociation equation is shown here, where H2O can break up into H plus OH minus. And we'll talk more about water in a little bit later in this video. Acids and bases are based off of 3 theories, and we're going to talk about 2 of the theories in this video. The third one you will learn about if you move on to AP Chemistry. The first one we're going to talk about is Arrhenius acid, Arrhenius base theory. This theory tells us that for Arrhenius acid, it dissociates into hydrogen ions in water. Now, Remember what dissociation means. It means separation of ions, right? And so when an acid dissociates, you have your hydrogen ion, and sometimes this hydrogen ion is called a proton, okay? So it dissociates into hydrogen ions, and then the anion part is whatever it consists of, right? So it can be a sulfate ion, SO42-, it could be a chloride ion, Cl-. In fact, if you take a look down here, this is an example of hydrochloric dissociating into hydrogen ion and chlorine ion. Well, it's actually a little bit more complicated than that. You see here it says that the hydrogen ion can be written as H3O+. This is called the hydronium ion. And basically this has to do with water. Now, if you think about the Lewis dot structure of water, oxygen has these lone pairs, and oxygen is actually partially negative, right? Whereas hydrogen is partially positive. And so there's this attraction there where if there's a free-floating hydrogen ion, then that hydrogen ion and the oxygen will attract, and that's how you get the hydronium ion. But I'm not really going to go into that into this video. You'll learn more about that if you move on to AP Chemistry. But we can pretty much write the hydronium ion, H3O+, as H+. Now, as for the Arrhenius base, the theory tells us that the base dissociates into hydroxide ions in water. So that's why we said it contains hydroxide ions when we were looking at the previous slide. So if you look here, sodium hydroxide, it dissociates into Na+, plus OH-. Now, the good thing is that by this theory, it's easy to figure out which substances are acid and which substances are base, right? So if it has a hydrogen and it begins with hydrogen, we label it as an acid. If it ends with a hydroxide or it contains a hydroxide, we label it as a base. However, the thing is, not all bases actually contain hydroxide. For example, some carbonates. We define as bases. And so that leads us to our second theory, the Bronsted-Lowry acid, Bronsted-Lowry base theory. Now, this theory tells us that a Bronsted-Lowry acid are proton donors. So remember, proton is just another word for hydrogen ion, and bases are proton acceptors, okay? So if you think about it, acids, there's a larger concentration of hydrogen ions, so it'll donate those hydrogen ions, whereas bases will accept those hydrogen ions. And from this, we have our conjugate acid and our conjugate base. So the conjugate acid is a species produced after the base has accepted a proton, and conjugate base is a species remaining after an acid has lost a proton. So if you take a look at this example, we have our acid, which is hydrochloric, and in this case, water is going to act as our base, okay? And now if you look on the right side of the arrow, we see that there's a hydronium ion, H3O+, and a Cl-. Well, can you figure out what happened here? So this right here, HCl and Cl- is a pair, okay? So what happened in this pair? Well, the hydrogen went away, right? So this acid donated its hydrogen ion, okay? So it donated a proton, and what took that proton or hydrogen ion? The water did, right? Water took the hydrogen ion, which now gives us H3O+. So H3O+ is our conjugate acid, while our Cl- is our conjugate base, okay? Now they differ by one proton, one hydrogen ion, no more, no less. And we're gonna go through some examples together in a little bit. These are some examples here that show you acids and bases and conjugate acids and conjugate bases. So as you can see here, we're using water, and water is on the top part is our base, water on the bottom part is our acid. So up here we can see that water is taking the hydrogen ion, it's taking the proton, and that's why our conjugate acid is the H3O+, And if you look at the conjugate base, the acid lost, right? It donated that proton, and so we have one less hydrogen here. On the bottom two examples, the water is acting as an acid, and so the water will give away a hydrogen ion, it will give away a proton, and look at what the NH3 does. The NH3 took one of the hydrogen ions, one of the protons, and now the conjugate acid is NH4+, while the conjugate base is OH-. So water can behave as an acid or base, so we call water amphoteric. Let's take a look at these practice problems. List the conjugate base for HCl. So remember, conjugate base means the species after it has lost the proton, okay? Because remember, acids want to donate their protons, donate an H+, okay? And so keep in mind that a hydrogen ion has a charge of +1, okay? So you have to keep that in mind for the overall charge. So for HCl, if it loses that hydrogen ion, what's going to happen? You're left with chlorine, and the overall charge is -1. H3PO4. You lose a hydrogen ion, then now you only have 2 hydrogens, right? And it becomes H2PO4-. H2CO3. If it loses that hydrogen, now you have 1 hydrogen left, and the overall charge is -1. Let's list the conjugate acid for SO4 2-. So what is this? It means that it accepted a proton, right? And so once it does that, now for SO4 2-, it's going to take a hydrogen or hydrogen ion. So now it has 1 hydrogen, and how does the overall charge change? It becomes -1. What about the next one, HSO4-? Now it's H2SO4, and what's the overall charge? It's neutral. Last one, NO3-. So it takes a hydrogen, and now we have HNO3 and an overall charge of neutral, okay? So let's take a look at this example. Let's label the Bronsted-Lowry acids and bases and conjugate acids and conjugate bases in the following reactions. So you have to look at the overall picture, okay? So look on the left side, look on the right side, try to pair them up, okay? So let's see. Here we have HNO2 plus HS-, and then on the other side we have NO2- and H2S. So obviously these two are a pair, and then these two are a pair, and I'm basing that on the nitrogen and the sulfur, right? And so let's look at what happened. HNO2, what happened on the other side? It lost it. It lost the hydrogen, right? And so that would make this our acid, and then this species our base, okay? So if this one lost it, this is now its conjugate base, and this is now the conjugate acid. Let's take a look at this one. So we can see here that these are a pair, the HSO3 and the H2SO3, and the HF and the F- are a pair, right? And so which one is the acid and which one is the base? So make sure you're looking at the overall equation, right? Here we have HSO3-, and it gained a hydrogen, okay? Whereas here we have HF, and what does it do? It loses that hydrogen. So out of these two, which one is the acid and which one is the base? HF is the acid, and HSO3- is the base. So on the other side, which one is the conjugate acid and which one is the conjugate base? F- is the conjugate base, and H2SO3 is the conjugate acid. Now in one of our previous videos, the solutions video, we talked about electrolytes and how solutions can be strong electrolytes or they can be non-electrolytes, and that all depends on dissociation. So again, dissociation means separation of ions. If there's 100% dissociation, 100% of separation of ions, solutions were strong electrolytes, and if there was no dissociation, then solutions were non-electrolytes. And one of the tests that we talked about was just the simple light bulb test, right? Strong electrolytes will light up a light bulb very strongly, and non-electrolytes won't light up the light bulb at all. And so for acids and bases, they can partially dissociate or they can completely dissociate to form ions. And it all depends on their strength. Strong acids and strong bases form strong electrolytes. So there is 100% dissociation. Some examples of strong acids include nitric acid, sulfuric acid, and hydrochloric acid. Strong bases include barium hydroxide and all group 1 hydroxides. So remember, group 1 is the first column on the periodic table. So for example, like sodium hydroxide and potassium hydroxide. And then there are weak acids and bases that form weak electrolytes because there's only partial dissociation. So there's only a little bit of separation into ions. So a couple examples of weak acids include carbonic acid and acetic acid, and a weak base is ammonia, NH3. So I'm going to show you this PhET simulation to show you what I mean by complete dissociation and partial dissociation of acids and bases. So for a strong acid, if you take a look here, the HA represents the strong acid, and it dissociates into A- and H3O+, which we can think of as H+, okay? And so here on a molecular level, it shows you A- and H+ here in the red, whereas if we were to compare this to a weak acid, you see that there isn't a lot of dissociation, right? You still see a lot of the original form of the acid here, and a little bit of blue and a little bit of red. So this is partial dissociation, partial separation of ions versus complete dissociation of ions, okay? Same thing for our strong bases and weak base, okay? So you can see the difference there, right? Complete dissociation, partial dissociation. So what does this mean in terms of our simple test for strong electrolytes versus weak electrolytes? Well, if we have a strong base and we stick these electrodes in here, our light bulb lights up completely, whereas a weak base, you see how dim the light is? Okay, so that's the difference there. And the same thing, weak acid, dim light, strong acid, bright light. So next we're going to talk about the pH scale, and as I mentioned before, the pH scale is from 0 to 14. If a substance is reading a pH level of 0 to 2, then we consider that very acidic. So we have strong acids there, and then we have weaker acids, slightly acidic. Here we have neutral at pH of 7, and then anything above 7 is basic, right? So if it's a pH of 14, then we say that is very basic. That's probably a strong base, as opposed to like 8 to 10, it's slightly basic, it's probably a weaker base. So this scale is showing you different examples of substances that we have around the house, substances that we consume. So milk you see here is actually slightly acidic. Some of you guys might think that milk is a base, but it's not. So a lot of our acids, or a lot of our foods and drinks are more acidic, okay? Blood is slightly basic. A lot of these are cleaning products or medicine. Okay, milk and magnesia is like a medicine that helps you go to the bathroom. Some other examples I'm gonna show you with this simulation. So this is showing you just different pH levels. So water, we have a pH of 7. Here's drain cleaner. Drain cleaner has a pH of 13. Hand soap is pH of 10. I'm trying to show you examples that we didn't see in the slide. Spit is slightly acidic, or slightly basic at 7.4. Chicken soup, pH of 5.8. Let's see, vomit, I'm sure you're curious, has a pH of 2. Now, pH is actually power of hydrogen. So pH, yes, it tells us, simply put, how acidic or how basic a substance is, but it's actually directly related to the number of hydrogen ions. It's directly related to the concentration of hydrogen ions in a substance. So here on this scale, and we'll talk about the bottom part in a little bit, but pH, we see our normal 0 to 14, and right above it, this is the hydrogen ions, a concentration of hydrogen ions. So the brackets is just another symbol to indicate concentration, so molarity, okay? So if we have the brackets, we just don't write the unit molarity. So here we see that when the pH is low, meaning more acidic, the hydrogen ion concentration is high, okay? Because remember when we talked about acids, right? Acids are known for their hydrogen ions. They contain hydrogen ions. So the more hydrogen ions they have, the more acidic the substance is going to be. As opposed to if you go all the way to the opposite side of the scale, add pH of 14, which we know is very basic, we can see that the hydrogen ion concentration is very low. It's 10 to the negative 14. Now the mathematical relationship between pH and the concentration of hydrogen ion is this. pH is equal to the negative log of hydrogen ion concentration. pH is the negative of the base 10 logarithm of the concentration of hydrogen ions in solution. Now I know what you're thinking. Oh dear God, she's using log. We're going to use log somehow. I promise you it's going to be easier than that. And you guys also have your calculators. You guys, if you look at your TI calculators, you have your log button, right? That's what we're going to use, okay? And then on the other side, we have POH. Now, if pH tells us the power of hydrogen, what do you think the POH will tell us? Power of hydroxide, right? So if you look at this scale here, POH is actually the complete opposite of pH, okay? And POH is related to the concentration of hydroxide ions, all right? So if you take a look here, when POH is 14, meaning it's very acidic, okay, your hydroxide ion concentration is very low. But in a very basic solution, we go to the opposite end, if the POH is 0, it means that the hydroxide ion concentration is very high, and they're complete opposites. Now, it's not this scale that I want you to memorize, but here we have the other relationship. POH is equal to the negative log of the hydroxide ion concentration. So we talked about two relationships. The first one is the relationship between pH and the concentration of hydrogen ions. The second relationship is POH and the concentration of hydroxide ions. The last one is the relationship between pH and POH. Now remember, I said that the POH is completely opposite of pH, right? And you can see that in the scale. pH is going from 0 to 14. When pH is 0, POH is 14. When pH is 2, POH is 12. Well, the third relationship here is that pH plus POH is equal to 14. Now the other thing I want you to notice before we move on to our practice problems is if you look at these numbers for the concentration, they are very, very small numbers, right? 10 to negative 6, 10 to negative 9, 10 to negative 14. These are really small numbers, okay? Now, as we go throughout these practice problems, keep in mind that these are the three relationships, mathematical relationships that we're going to use. pH plus POH is equal to 14. pH is equal to negative log of the hydrogen ion concentration. POH is equal to negative log of the hydroxide ion concentration. Now, I don't know if you talked about the log function in your math classes yet. If you didn't, on your calculator, you'll see a log function. It's one of the buttons on your TI calculator. That's all you need to use to solve these problems. Number 1, what is the pH of a solution with a hydrogen ion concentration of 1 times 10 to negative 4 moles per liter? Well, I'm going to use the formula pH is equal to negative log of H+. I'm going to go ahead and plug in my concentration, and with my calculator, I'll plug in negative log 1 times 10 to negative 4, close your parentheses, and you get a pH of 4. Number 2, what is the hydrogen ion concentration of a solution with a pH of 6? Well, again, I'm going to use the same formula, right? But I can rearrange this formula to solve for the hydrogen ion concentration. And keep in mind that this is a base of 10 logarithm. So if I were to rearrange it, the concentration is equal to 10 raised to the negative pH. So let's say I don't remember that formula, right? Let's say I don't remember how to do that. Well, you can go ahead and plug in your number. 6 is equal to negative log of hydrogen ion concentration. Let's replace H plus with X. Previously, I know some students got confused by just leaving it as H plus, so I like to just put an X in there. And then, again, base of 10 logarithm. So this would rearrange to look like this, 10 to the negative 6. And that is what the concentration is. Right? If you need your calculator, this function, the 10 raised to the number, it's second log on your TI calculator. And you would do second log, negative 6, close your parentheses, and you get this as your concentration, 1 times 10 to negative 6 moles per liter. Number 3. What is the pH and pOH of a 1 times 10 to negative 8 molar solution of sodium hydroxide? Well, before you rush and plug it into the pH is equal to negative log of hydrogen ion concentration, pause for a sec and look at the concentration of this solution. It says 1 times 10 to the negative 8 molar solution of sodium hydroxide. Well, what is sodium hydroxide? It's a base. So instead of plugging it in to solve for the pH, we will plug it in to pOH is equal to negative log the hydroxide ion concentration. This is of base. Okay? Whereas number 1 and number 2, the pH was given and I asked for hydrogen ion concentration. We know that mathematically those two are in direct relationship. So if we're given a base like sodium hydroxide, then we will find the pOH first. So we're going to go ahead and plug it in, and the pOH is equal to 8. And then we're going to plug it into our pH plus pOH is equal to 14 formula, right? And pOH is equal to 8. We're going to subtract, and pH is equal to 6. Last problem. pH of an unknown solution is 6.35. What is its hydrogen ion concentration? So again, we're going to use the formula pH is equal to negative log of the hydrogen ion concentration. We'll rearrange it to look like that. And we're going to set it up, and it's 10 to negative 6.35. Well, I don't know if you noticed the pattern or if you noticed the trick in our problems 1 through 3. Well, going back to problems 1 through 3 before I get to number 4, when we're solving for the negative log of our concentration, our answer is simply the same number as the exponent there. Okay? Over in number 2, pH is 6, well, our exponent is that pH. It's 10 raised to the negative 6 power. And we can do that when the pH is a whole number like this. However, when the pH is a decimal number like this, 6.35, well, plug it into your calculator. How is this answer any different from plugging in times 10 to the negative 6? 10 to the negative 6 will simply be 0.000001, right? And that is 10 to the negative 6. But go ahead and do this now. Second log negative 6.35, or 10 raised to the negative 6.35. What do you get? Yeah, you don't get a pretty number like 0.000001. You get 4.47 times 10 to the negative 7 moles per liter. When it comes to acids and bases, one lab technique that we do is called a titration. A titration is the slow addition of one solution, for example an acid, where we know the concentration, to a known volume of another solution, like a base, where we don't know the concentration, until the acid and base reach neutralization. So do you remember when we talked about neutralization reaction way back in our reactions unit? a neutralization reaction is when an acid and base react and it produces an ionic compound in water. For example, we have magnesium hydroxide and hydrochloric acid. Well, magnesium hydroxide is our base, we have our hydrochloric acid, and when these two react, it will form an ionic compound, magnesium chloride, which we know is also known as a salt, and water. And for all neutralization reactions, this is what we get. We always get an ionic compound and water. Well, in a titration, we use an equipment called burette. And a burette is basically like an upside down graduated cylinder. Okay? So here, if you look at this picture, here's our burette. This is how we stop the solution from coming out. And then down here, we have our flask. Okay, so usually we put our base in our burette and we have our acid in our flask. We know the concentration and the volume of our base, and we know the volume of our acid, but we don't know the concentration of our acid, and that's what we want to figure out in a titration. So a graduated cylinder, if you think about it, it goes from 0 all the way up to 50, right? Or all the way up to 10 or 100. And that we already know how to read. A burette is the opposite. Burette, the 0 starts up here and it goes down to 50 here. Why it's like that? It's because the solution flows down, and so it's easier to read that if it's going down, all you have to do is read it basically backwards in a sense. Okay, so if you look at this close up here, this is not reading like 40.7, right, like we're used to doing with the graduated cylinder. Instead, it's the opposite because it increases as it goes down, so it's 39.123, 39.3, okay? Now I'm going to show you a video of a titration.
A titration is a controlled acid-base neutralization reaction. 20 milliliters of hydrochloric acid of an unknown molarity is added to a flask. 2 drops of indicator dye are added to the acidic solution. This indicator dye is clear in acidic solution and pink in basic solution. The burette is filled with a sodium hydroxide solution of known strength, and an initial reading is taken. The base is added to the acidic solution until the solution stays a slightly pink color. At this endpoint, a final reading is taken. The moles of base added equal the moles of acid present. This same reaction can be followed using a pH meter instead of an indicator dye. Initially, the pH changes very little as base is added. Suddenly, the pH changes rapidly as the endpoint passes. The solution quickly becomes very basic, and again the pH changes very little. The endpoint occurs at this middle point on the curve.
So in the video, you saw that the titration stopped when the solution turned pink, right? And so there are different indicators. So an indicator is added to an acidic solution to tell us when to stop our titration. So for example, for phenolphthalein, when you put phenolphthalein into an acidic solution, it's colorless. And once you get to what we call an endpoint, which I'll talk about next, it'll start changing color to pink. And that's basically when you want to stop your titration, because that's where you reach the end point. And again, I'll talk about that in a couple of seconds. If you go past that end point, then your pink color will just start to turn like hot pink or bright pink. And there are different indicators that we use. There's, for example, thymol blue, where it goes from yellow to blue. There's bromothymol blue, again, yellow to blue. Phenol red, which goes from yellow to red. And then there's methyl violet, that goes from yellow to violet. So as you can see, it changes based on the pH as well, okay? So this is what a titration curve looks like. So you saw this in the video as well. On the Y we have pH, on the X we have the volume that's added. And here you see that this is our starting point, and this is, because it's low in the graph, it's telling you that we were starting with an acid, right? Because the pH is pretty low. And as we start to add a base, you see that the pH starts to increase and it shoots up because we pass this end point, and then it becomes basically more basic because now we've added more base. So at this point here, this is called the equivalence point. The end point in the titration is telling us when to stop our titration, so we're looking for the color change, which is called the end point. On the graph, this is called an equivalence point. And the equivalence point, by definition, is the point at which moles of hydrogen ions from the acid is equal to the moles of hydroxide ions from the base. This is the stoichiometric point of titration. So at this point right here, this is telling us that we need to add this much volume in order to neutralize our acid or base solution. After we've completed our titration, this is how we calculate the concentration of the acid. So, for example, in this question, 30 milliliters of 0.1 molar sodium hydroxide neutralize 25 milliliters of hydrochloric acid. Determine the concentration of the acid. So the first thing you have to do is come up with a balanced reaction. So remember, acid and base will always make an ionic compound and water. So for number 1, I gave it to you, and this is a balanced reaction. So we are going to start with 30 milliliters of sodium hydroxide, okay? So we are going to look at the volume and the molarity of the sodium hydroxide, and then we will look at the stoichiometric relationship, or in other words, the mole-to-mole ratio of our base to acid, and then from there we're going to use our volume to figure out the concentration of the acid. So remember that molarity is moles per liter, right? But we're given a volume of milliliters, so we want to go ahead and convert our volume to liters. So we're going to bring down milliliters, and liters will go up, and we have 1,000 milliliters is equal to 1 liter. So now that we have converted our volume of sodium hydroxide to liters, we're going to go ahead and now use the molarity. So we're going to copy down liters, and we're going to put moles on top, and this right here is our molarity of the sodium hydroxide. So it's 0.10 moles per liter. So remember how you plug that in? 0.10 moles over 1 liter. Okay? And then from here, we bring down moles of sodium hydroxide, and where are we going to go at this point? Well, now from here, we're going to look at the stoichiometric relationship between our base and acid. So we're going to put moles of hydrochloric on top, and remember where we get moles over moles, that's our molar ratio. We're going to look at our coefficients, that's 1 to 1. And then in the next fence, I want you to think about what we are trying to find, okay? For right here, if we were to cross out our like units, we're left with moles of hydrochloric. Well, we want the concentration, which is molarity, which is moles per liter, right? So we're going to put the volume of hydrochloric acid down on the bottom of the fence, and that way we get moles per liter. Well, right now it's 25 milliliters, so what do we have to do to this number here, this volume here? We're going to go ahead and convert that to liters, right? Because again, we want moles per liter, moles over liters. So we want to make sure that our units all match up. And here I'm not going to do the fence, I'm just going to simply convert my volume by dividing by 1,000 to get my liters. And if you see here, all of my like units will cancel out except for moles and liters. And when I look at the units, it should really match up with my end unit. So moles here should match up with my top unit here, and then liters needs to match up with my bottom unit here, right? Because this is written like a denominator and that's written like a numerator. And once you plug this into your calculator, you will get a molarity of 0.12. So again, you can leave it like this, 0.12 moles per liter, but again, moles per liter is the same thing as 0.12 m, okay, for molarity. Let's take a look at number 2. How much of 0.50 molar nitric acid is needed to neutralize 25 milliliters of 0.05 molar calcium hydroxide solution? And here, I took away the products because I wanted you to find the products. So go ahead and determine what the products are going to be. Remember that for a neutralization reaction, we always have water as one of our products. And our other product is going to be what? Well, you can simply pair up these two, right? Outside, remember? And then inside. So here we have calcium nitrate. But remember, when you write it, okay, keep in mind your oxidation numbers. So calcium is 2 plus, nitrate is 1 minus, and that's how we get calcium nitrate, okay? Be sure to balance it at this point. And to help you balance neutralization reactions, you can switch out your water, H2O, and write it as HOH. And remember, that way you can keep your hydroxides together, and it's much easier to balance that way. So if I do that, I need a 2 in front of the HOH because I have 2 hydroxides here. And then I'll need a 2 in front of my nitric acid, and that takes care of the balancing. So I'm going to go ahead and rewrite my HOH as H2O and go ahead and solve the problem now. So we are going to start with the volume of our base. Okay, so you always want to start with the pair that's given, and in this case, that's the base. So 25 milliliters, and here we're going to go ahead and convert, okay, into liters, right? Because again, molarity is moles per liter. And then I'll use the molarity of calcium hydroxide. And then from here, now we're going to look at the stoichiometric relationship, or in other words, the mole to mole ratio of our base to acid. So here it's 2 to 1. And think about now what it's asking for. It says how much of this acid do we need? So now we're going to use the concentration and put it into the fence. Okay, so here we're still going by, we're going to bring down the same unit here, so moles and moles, okay, and that way we're going to put liters on top, so we're basically flipping our concentration, all right, and then we're going to go ahead and plug in our number, 0.50 moles, and then 1 over 1 liter, so that goes on top. Our like units will cancel out, multiply and divide, and we get 0.0050 liters. Number 3, if it takes 455 milliliters of 1.5 molar calcium hydroxide to neutralize a spill of 2 molar sulfuric acid solution, what volume of acid was spilled? Now for this problem, I want you to go ahead and pause the video and try it out yourself. Keep in mind that you always need a balanced reaction for titration calculations, so start there. Acid and a base make water and an ionic compound. And then go ahead and try to set this up on your own. Go ahead and play the video when you're ready. This is the balanced reaction that you should have written down. Calcium hydroxide plus sulfuric acid yields 2 moles of water plus calcium sulfate. And again, the order of this doesn't matter as long as the reactants are on the reactant side and the products are on the product side. Once you set it up, you should have something like this. So what I did was, in my fence, I went ahead and converted my milliliters to liters. And then I have my molarity of the base. I have my mole to mole ratio. And then I have my molarity of the acid. And you get an answer of 0.34 liters. And that's it for acids and bases.